All right, I'm going to talk about the .NET garbage collector. And the plan of the talk is sort of to talk about everything in the sense that I'm going to talk first about the principles. How exactly does it work? What does it do? What are things like GC generations? What is server GC? What is background GC? And so on. I'm going to talk about how both hardware and software are changing, what this means for us, and how we're trying to adapt and make things better. And finally, I'm also going to talk about how to diagnose GC problems. So explain how to look at things in purview, what SOS and CLRMD might be good for. And lastly, I'm going to point you to some resources where you can find more interesting information. All right. So the principle of our GC is that it's a tracing GC, which means there are certain locations that are immediately accessible to the program. Is the mic still on? Yes. Like stack locations, in other words, your local variables. Registers, which are also just your local variables in C#. There are static fields. There are GC handles. And finally, there are finalizable objects, which are special because they need to survive. Even if they're not referenced by anyone, they need to survive into the next cycle because their finalizers have to execute. So to give an example here, if you have a static field, is the mouse visible here? Yes. A static field that points to object B, and object B points to object E, and object E points to object F. That means all of these objects need to stay alive. Now, what I also want to point out is the objects that survive are the objects that the program could still get to potentially. It doesn't mean your program will still use them. And because, as you see in the picture, when we trace all these objects, the time it takes the garbage collector to trace the objects will of course be related to, first of all, the number of the objects and also the number of the pointers between them. And so if you, for instance, know that something you're pointing to from, say, an object's field is no longer necessary, it may sometimes be advantageous to null it out. Don't be very anal about it. Don't do that in every time, but sometimes it may be useful, say, if you have a big table, a big hash table, say, that you're no longer using, it may be useful to explicitly null out the reference to it. All right. So the first step the GC does is to find out all the objects that are still being potentially used. The second thing is either we compact the surviving objects or we just put the free space onto a free list. The first we call sliding compaction because we don't scramble the objects while we do that. Instead, we move them down as a unit and basically squeeze out the holes between them. So for compaction, we actually have several steps that we have to do after the initial marking. The first step we call the plan phase, and this is where we figure out where the objects will go after the compaction. And so we basically annotate the objects with their future address. The second step is we change all the pointers, not just in the GC roots, but also in other objects. This is called the relocation phase. And the last phase is where we actually copy the objects towards lower addresses. The other process that we use is called mark and sweep, where sweep just means look at all the gaps between surviving objects and put those gaps as free spaces onto a free list. So this is potentially cheaper, and it also enables background GC. And the way background GC works is it essentially takes a snapshot of the GC roots, then lets the program run on, and in the background it figures out which objects are reachable, and then it stops the program again and basically does a final mark to see whether there's any additional objects that are reachable now. And then it lets, again, the program run. And in the background, it actually does the sweep phase and puts all the free spaces on the free list. What we currently don't have, but what we're thinking about, is concurrent compaction. The problem is then you run the program while in the background you're compacting, and that puts some additional overhead on the program that is running. All right, so why are we doing compaction at all? We're doing compaction because of two reasons mainly. One is because compaction creates large free spaces, we can now very efficiently allocate. It makes a big difference in performance whether you allocate from a free list or whether you allocate by just incrementing a pointer. The second reason is that it very much reduces fragmentation. It doesn't completely eliminate it in our setting because typically you have pinned objects that you cannot move. And so there will be some fragmentation around those pinned objects. All right, so this was the principle, but of course our garbage collector is much more complex than this simple picture. So first of all, we have what is called a generational GC. That is based on the observation that most objects actually die very young. So we create these objects in a region that we call generation 0, and that is collected very frequently. And of course, you may have older objects that point to younger objects, and you treat those essentially as additional GC roots. All right. So when generation 0 is collected and you find some surviving objects, they get promoted, as we call it, to the older generation, and then they get checked less frequently. And when a generation 1 GC happens and still objects survive, then they get promoted to generation 2, which is collected even less frequently. And usually, by default, we collect generation 2 in the background because it tends to get large for most apps. All right. Now, I mentioned that we need to basically treat pointers from older generations into younger generations as GC roots. And in order to do that efficiently, we need to know where they are. If we needed to enumerate the whole generation 2 and 1 just to collect generation 0, it would be too slow. So we have this additional table here called the card table, which is essentially a side table consisting of bits that tell you where in the older generations you have pointers to younger generations. And I should phrase it more precisely, where you potentially have pointers, because we actually turn on more bits than necessary during writes into older generations because of performance reasons. And the reason is simply turning on a single bit is expensive in a multiprocessor configuration because you have interlocked instructions which are expensive, and so we actually turn on a whole byte rather than a single bit. And later when the GC runs, it figures out which bits were actually unnecessary and turns them off. So there's this side table here. There's another side table called the brick table, and that has an interesting role, and it's really motivated by C# language features. It has what is called references, and references may point into the middle of an object. Now, to the GC, that's not very useful because the data that it needs to keep track of whether an object is marked or not, that's really associated with the beginning of the object. And so from a pointer into the middle of the object, it has to go back to the beginning. And rather than search from the beginning of the heap for the start of the object containing an interior pointer, it wants to do that more efficiently. And that's what this brick table is being used for. I won't go into the exact implementation of it because it's a little bit tricky and I don't think it's of interest. One thing I haven't mentioned is there's also this separate thing on the right called the large object heap. And its reason for existence is twofold. First of all, large objects are not typically, no, I should phrase this differently. Large objects tend to survive for longer. That's the first reason. And what was the second reason? Sorry, it escapes me now. Okay, let's move on. we have something called server GC, and what this is essentially multiple heaps, by default one per processor, and they all consist of the generations that I have already talked about and a large object heap. And I have drawn them slightly different sizes because that's the situation that will typically happen in practice. Even server applications, if they handle the exact same load on each processor, they will never turn out the same. And the reason this is a problem is we have GC threads that are basically working on each of those heaps. And if the heaps, their allocation, their size is unequal, then there will be an unequal amount of work for these server threads. And during GC, we actually do GC in lockstep on each of those heaps. And there are certain phases in GC where those GC threads have to synchronize. That means that, say, after the mark phase, all the threads will have to wait until the last thread has finished marking, because you cannot figure out where the objects will go before you have the marking complete. You could do this if the heaps were isolated, in the sense that there can be no pointers between them. But in C#, there's no way to express this, so we have to assume the pointers really go in all directions between those heaps. So there's no isolation at all. And that also means that, you know, the GC thread that takes care of heap number 0, it will actually trace pointers into all the other heaps as well. And so they all step on each other's toes, so to speak, all the time. But that doesn't really matter, because the way the code is written, it's all idempotent, in the sense that if an object is marked, you know, you may have two threads finding it not marked yet, but they mark in parallel, but nothing bad actually happens because everybody just sets the mark and they don't actually cause problems. All right. So the important takeaway is that for server GC, maintaining some balance is actually important, and that's not something you can do in your app by writing C# code, but that's something we have to do both during allocation and also during GC. And there's actually some work in progress to improve that balancing. All right, so that was about server GC. And I also want to mention that again here we have background GC doing generation 2 collections, and that is because Gen 2 collections otherwise would be too slow. Especially because the world is changing in the sense that memory sizes keep getting bigger. I think over the last 10 years or so, we have seen about a factor of 2 every 2 years in memory sizes. And that means that apps, the heap sizes that apps have actually also become bigger. And that means that Gen 2 collections become slower because the memory speeds are not increasing as quickly. And so, by implication, this means background GC is becoming more and more important, because for large heaps, say 30 gigabytes that I've seen, or 60 gigabytes, it will take several seconds to collect. And so doing it in the background is of vital importance. Another trend we've seen is we see more and more cores. And for server GC, that means more and more heaps. And that means balancing allocations between these heaps and balancing GC work becomes more and more important, because if you have a GC thread that takes much longer than others, it will block the others from progressing. And that will increase GC pause times. What's making things more complicated yet is NUMA architectures, where for, say, a GC thread or a user thread running on core 0, you know, there may be some memory that's more expensive to access than other memory, and so you have to make sure you pick the correct heap depending on a conflicting set of objectives. You want to keep the heap heaps balanced, yes, but you also want to allocate in memory that's reasonably cheap to access for the processor you're allocating on. And so it becomes very complicated to do a good job here. The next trend that I want to mention is almost the opposite, in the sense that containers are a smaller world in itself, and so they may run on a smaller set of cores with less memory, and so it's a smaller world in itself that we still need to work on well. Similarly, microservices mean that you have multiple applications working on the same box, working together, exchanging messages, and also depending on each other. And so if one microservice has a large GC pause, that may cause all the other ones to be blocked and waiting for a response for the one that is blocked right now. So this means potentially stricter latency requirements in the future. Lastly, we have a big trend on working really well on Linux, and that caused some issues because Linux works differently in many aspects. For instance, in Linux, as it's configured normally, you can overcommit, which means you can commit memory and it seems to succeed, but as soon as you touch it, you can get out of memory, so you have new failure points. On Windows, we were using a feature called Write Watch, which means the operating system has an API that can tell you which pages were written to. And we use that in two contexts. One is for background GC, because if you write to objects, this means the connectivity of your object graph can change. And so for the pages that got written to, you actually have to catch up at the end of a background GC. Secondly, we use it to make sure that we don't look at more areas in the card table that I mentioned than absolutely necessary. So we have sort of a superstructure that tells us which pages in the card table can even contain set bits. And so these two aspects have to work differently on Linux. Lastly, thread priorities work differently on Linux. While there are higher priority threads, currently our server GC threads on Linux are normal priority, whereas on Windows, there are high priority. So there are some changes, and we're trying to adapt and work well on Linux, but there are some issues. But I think with 3.0, we're actually in pretty good shape. All right. There are some things we have been doing that are improving things, and that were motivated mostly by our internal apps. For instance, we added large page support, which means that the GC heap can now use large pages. And the reason this helps is the processor internally basically has a small buffer for the page table entries that it uses frequently. That's called the TLB, the translation look-aside buffer. And that has a limited size. And so because the heaps are getting bigger, it puts more load on the TLB. And if you use large pages, you need fewer page table entries. And that actually helped the Bing front end quite a bit. A metric called the P95 latency improved by 18.5%, the P50 latency by 9%. These numbers mean 95% of the requests are below this latency. We also improved background GC. We heard that with larger heaps, background GC becomes more important. There was an issue where, while the background sweep was actually happening, we couldn't allocate from the large object heap. The reason was that the sweeping updates the free lists. The free lists are protected by a central lock on each heap. And of course, allocation from the large object heap also needs to take space from the free list. It needs to inspect the free list. And so it had to wait for that lock to be released. Now, what an important observation here is that the large object heap sweeping actually takes much less time than the small object heap sweeping. And so we just split those locks and made separate locks for the small object and the large object heap. And so large object allocation only needs to wait for the large object heap sweep to finish, which is typically much shorter. That again had a big impact on the Bing backend this time. It reduced the latency by about 10%. Another set of changes is associated with containers. In 2.2, we didn't do a very good job allocating heaps to containers, and there were situations where we would basically run out of memory right at the start if you set your hard limit low enough and the number of CPUs was large enough. And now we do a much better job reserving memory upfront and dividing it the right way between GC heaps, and also we limit the number of GC heaps if the hard limit is reasonably small. A second change is because containers typically have smaller limits in the amount of memory they can use, we now compact the large object heap by default, while normally this is not happening. There are some new configs that I'm going to go into some detail later. I'm only going to single out the GC Hymen % because that's not what I'm going to talk about later. Typically what happens is when the memory load is at 90%, GC goes into a special mode where it says, oh, now I have to pay attention. If a Gen 1 collection would increase Gen 2 size, I'm going to collect Gen 2 as well. And that limit is normally set at 90% by default, but you can adjust it if you find that your application does not behave well with that default setting. We also invested heavily in diagnostic tools on Linux. We already heard that during Adam's talk, what tools are available. And one thing that is currently being worked on is to make the heap balancing better that we talked about when we discussed server GC. And that's both during allocation and also during GC. So what we do during GC is some work stealing in the mark and in the relocation phase. So GC threads can help out each other if one thread is taking much longer than others. All right. What we will focus on in the future is to try and keep reducing GC pause times, especially in server GC, where we have more opportunities because of the balancing can just get better. And also allow users to communicate better which perf aspects are actually more important to them. You can have apps where keeping the memory footprint down is really the most important thing. There are apps where minimizing the total time spent in GC is most important. Say a batch process that just processes some data and then stops. You typically just care about how long that takes overall. There are also apps that are in some sense interactive. Say a thing that has a UI, a web server, there it's typically important not to have any long pauses. And so where it's important to keep the individual GC pauses smaller. This is a little bit tricky because typically it's not all or nothing. Typically you want to strive for some compromise between all of these different objectives. You want to keep, say, the memory footprint down while keeping pause times reasonable and so on. And it's not trivial to find a way to express this in a good way. Finally, I'm going to talk about how to start investigating GC performance to find out whether you actually have a problem with GC pauses, say, or whether you are actually allocating too much. My favorite tool is Purview. That's what I use all the time. And the numbers that I look at, you reach at going to memory group GC stats. I misspelled that. There's actually a space here. I'm sorry. The first number I look at is typically the time paused for garbage collection. I should mention this thing. That's a trace file I took for an ASP.NET benchmark. I'm saying explicitly benchmark because that means it's probably more simple than a real app. And here we spent 3.1% of our total time in garbage collection. And I find this number important because it gives you an upper limit on what you can achieve by making the job of GC easier. In the beginning, I mentioned that the time spent in the mark phase and the time spent in GC overall is related to the number of pointers you trace and also to the number of objects that survive. And so if you want to trim down pause times, you would have to look at how many objects survive and why and so on. And also how many objects get allocated in the first place. So while I find the 3.1% number somewhat reasonable, I would be concerned about the total allocation, which is 22 gigabytes. Now, 22 gigabytes is for a 30-second run in this case. This means we allocate about 700 megabytes per second, which seems to me quite high. So it would be nice to somehow reduce this. The third number I look at is just the overall GC heap size, and that's also something I recommend you look at because sometimes you see a process having a large working set and you think, oh, it must be GC. I urge you to actually measure with Purview and look at the numbers and make sure you have the right culprit. The next thing I look at is in the same page a little bit below this one, and it's the GC rollup by generation. And there you see how many GCs of different generations were done and how long they took. So the overall number here is over 230 GCs. And because the run was about 30 seconds, this means we do about almost 8 GCs a second, which is quite a bit. We do a lot of Gen 0 GCs. We also do quite a few Gen 1 GCs. And we do very few Gen 2 GCs. So what this tells me is, first of all, we have significant allocation. Second of all, there's also a significant amount of memory surviving into generation 1. And there's very little memory surviving into generation 2. So the next, if you wanted to optimize, the next step would be, so what are all the objects that survive into generation 1? And can I somehow reduce this? Can I hold on to less memory while a request is being processed and so on? I need to mention that this particular test also accesses a database. And so you can wonder about, oh, okay, so what happens to the request between the time when it asked for a response from the database until the response gets back? You know, if that takes a significant amount of time, what happens if a GC happens in between? Can I hold on to less memory while this request to the database is being processed? So that would be one thing that could be looked at. I also look at the pause times to make sure they're reasonable. Now here the mean pause times are actually very good, but I think that's partly because this is a benchmark and it's a little bit simpler than what you would see in the real world. In the real world, you would be quite happy to see sub 10 millisecond mean pause times. The maximum pause times are also important. And sometimes what happens is during the ramp-up phase, you will see larger pause times. So it's also important to look at, when in time the larger pause times happened, just because it's important not to get fooled by ramp-up issues. All right, so these are sort of the initial level of investigation to make sure I understand if I have a GC problem at all, and if I do, what exactly is it? So to show you some examples of what I've recently seen is an app where we had very many Gen 2 GCs. And what happened was they were triggered by large object allocations. And so the first step is really to figure out where these large object allocations are coming from and whether you can somehow reduce them. Now, assuming they're actually necessary, what you can do is set that GC LOH threshold higher. What the setting is typically, by default, the threshold for large object allocation is 85,000 bytes. That has been the same thing since '98 when I joined Microsoft. It has never been changed. However, with this GC LOH threshold, you can set it higher. And that is useful for the situation where you allocate many large objects, but they're very short-lived. And so if you set it higher, then that means more of these large objects don't go into the large object heap, they go into generation 0. And that may be advantageous if they die very quickly. It's especially advantageous if they themselves don't contain pointers. If they do contain pointers, then sometimes that would actually increase pause times. It would reduce the number of GCs probably, but increase your pause times, and that might be problematic in itself. The other thing you can do is consider using the array pool. In other words, pool your big objects and reuse them. Now, this is essentially manual memory management, and it's, of course, fraught with subtle correctness issues, especially in a multi-threaded environment where you really have to make sure you're not using one array for two different purposes at the same time. Otherwise, you will have subtle bugs that will take forever to track down. Another thing we've seen are occasional spikes in GC pause time. And that tends to happen when there's other high priority activities happening on the same machine. And because server GC uses all CPUs by default, and it actually needs them all to run, if you have another activity that takes one of those CPUs away, the other threads will get blocked from making progress, and that will increase your pause times. And so again, the first step is to investigate what takes CPU, make sure you understand whether the activity that's going on is actually necessary. And then assuming it is, and there's no way around it, you should consider setting the GC heap count setting to a lower value than the number of CPUs. Say you have 32 CPUs, then set it to 30 so that you leave some CPUs for other activities. Now, it's another setting that goes with this is to make sure you either don't hard affinitize GC threads to CPUs, that's the GC no affinitize setting, or you actually plan explicitly which activities should take which CPUs, and you can use the GC heap affinitize mask to do this. So, for instance, say you have a network driver or something that wants to run on core 0, you would make sure you don't run GC threads on core 0. Another thing I've seen recently was a large object heap, and it was a puzzle initially because it was 60 gigabytes in size, but only 5% of it was consisted of live objects. And so we initially thought, so is there some fragmentation going on? What's the reason? But no, it was different. During ramp up, the large object heap actually got to 90 gigabytes in size, but then almost all of the objects died in it. And so GC just shrinks from the tail, so to speak, of the large object heap, and it trimmed it down to 60 gigabytes or so, but it doesn't compact by default. And so if you wanted to trim down the amount of committed memory for this app, you would have to explicitly ask for compaction. Now, during that compaction, of course, you will incur a larger pause time, but for some apps, this may be worth it. Now, I've talked about Purview. What are other tools you can use, and when would you use them? Well, there's SOS. That's an extension to WinDBG and LLDB, and I would use it if I found, say, a memory leak, or I was just curious what's on my garbage collected heap. So in other words, to do statistics on what heap objects are actually live there, what's the distribution between types and sizes and so on. And also, if you have some type of memory leak, you typically want to figure out what path holds those objects alive that are growing. If you get into a situation where you have to do this repeatedly, it may be worthwhile considering CLRMD, because that allows you to essentially write C# code to walk your garbage collected heap, inspect data structures, figure out reference paths, and so on. So that allows you to do automation on the same things you were doing with SOS. So I would not start a performance investigation with SOS or CLRMD. I would use them as tools where I know exactly what I'm looking for. I would always start with Purview to figure out sort of what area I should focus on. All right. Finally, resources that I can point you to. For the internal workings of the GC, Konrad Kokosa's book is very good. I'm showing the link here to the publisher. There's also some internal documents from Microsoft that talk about garbage collection and performance. You can, of course, also look at the source code. And if you look at the source code, I would actually encourage you to look at Konrad's book in parallel, because he has some pointers to the source code, and you will better understand what pieces of the source code are supposed to do what their underlying purpose is. You can download Purview, and I would encourage you to do so if you're interested in Perf at all. It has many more features, as you've seen in Adam's talk. And I use it all the time also to look at subtle perf issues in GC and figure things out. And it has many features, and I have not managed to learn all of them yet. There's also Mauni Stevens' blog. Mauni has been the main dev on the GC for a very long time, and typically she writes blog entries when there's either some important investigation with general implications she has done that she finds interesting, or when she has added new settings or new features to GC that she wants to alert people to. So this is an excellent way to keep up to date with what's happening. Finally, there's the French company Criteo. Criteo is a French advertising company that runs thousands of servers under very tight latency constraints. And so they have had occasions to do investigations into garbage collector pauses and such. And there are some excellent blog entries that I want to encourage you to look at. And also they have done some nice YouTube video explaining how they do investigations, and how they go from one tool to the other depending on what tool is more useful to them. So all of these things are excellent resources. Okay, I think I've told you about everything I wanted to. Please shoot away with questions. I think we still have time.
Yes, we have time for, let's say, 1 or 2 questions. So if you want to ask a question, please raise your hand.
I'm coming with microphone.
One of the issues you talked about before was pauses in your application. Are there any plans to sort of implement something similar to like a Zing's sort of C4 algorithm whereby they have, they're able to sort of guarantee pause times of, around a maximum of around a millisecond under normal conditions?
Yes, we have thought about it, and we're still thinking about it, but the problem with these zero pause collectors are they are also imposing an overhead on the app. In other words, your app will run slower, and we're still thinking about how to strike the right compromise there. So yes, it's something we're actively thinking about. We also think, though, because of the perf impact, this will likely have somewhat limited applicability. There are not that many apps that really need pause times below, say, 10 milliseconds or so. There are some, to be sure, but not that many. Are you working on an app that has this problem?
Yeah, I mean, it's traditionally something that's, very useful in the capital market space. So, the people traditionally, if they're not using sort of managed languages, will use Java here and use Azul Zing. But I think there's there's a reasonable demand from capital markets, processing market data, sending orders, those kind of systems where it's really not acceptable to have a GC time above, say, a millisecond. And in that case, everyone has to go garbage free if they want to use C# in steady state. And it would be useful, I think, to have something that would support a sort of around maximum millisecond time.
So your application is broad area financial industry, say trading, analyzing market data, that sort of thing.
That's right, yeah.
Okay, thank you.
Do we have time for one more?
Yes, one more question.
Hello. You've mentioned that the server GC utilizes all the cores on the host on which it is being executed. So, assuming I have a Docker container with .NET Core on board, if I run that on a multi-core Kubernetes node, how will that affect all the other cores that are physically present on the node?
Actually, I don't know. I think for containers, you can probably say which cores they're supposed to run on, right?
I can definitely constrain the amount of CPU limits, but I'm not sure how that affects the GC usage.
I actually don't know either. I'm not familiar how exactly this works with containers. I know that you can restrict containers to use only a subset of the CPUs, and then we will honor that. But if there's just say a limit of overall CPU usage, then I cannot tell you how that affects GC usage.
Right.
Sorry.
Have we got one last question? Okay, one last question.
Who was faster?
Back row.
Okay.
Okay, so I have one question, like you mentioned now in Stevens before, and I've seen some documents on Course Lab about other type of heap, like you mentioned the large object heap, and I've seen some designs about like a pinned object heap as well, but I cannot see any more information about it because it can be beneficial for some kind of applications that mostly do interop with native code, and you want to pin your objects, and as you said, like it prevents compaction and causes fragmentation of the heap. I would like to know, like, what's the status of that? Is there some work that's being done for?
Yes, there is active work being done, and I should have mentioned that perhaps on one of my slides where I talk about what has been done and what is in progress. The pinned heap is definitely something that is in progress. I don't know the exact implementation state at this time, but yes, it's something we are actively working on.
Okay, thank you.